Good morning, everyone. For today, we have in store the fifth and final session on bioenergy technology. I still had a little part of the previous bioenergy technology training that I didn't quite manage to finish back then. It's more about space requirements. Following that, we'll be looking at operational maintenance issues and environment, health and safety. I had originally planned also to give you the solution of the case study that I presented during the previous session. That was on financial analysis. But I'm not quite sure if we managed to do that today, looking at the time. So if we have any time left, I will present those solutions. Otherwise, I'll present them next week. I should add that I didn't yet receive any solutions from any of you. I don't know if that is because there's some unclarity or if there's no time to make them as type of homework. Well, if you are in the opportunity to do it, then yeah, please do, because I think it's valuable to really start working with the training matter and get some start, some experience, and then also see what you run into, and then discuss that during the training. So I would really recommend you to do that. So yeah, let's start with where we ended during the previous bioenergy technology session. That was on storage, on space requirements and storage. I think I showed this example on the space requirements for storage of a say medium-sized CSP unit, the combustion plant and the steam turbine. Let's say assuming a certain quantity of biomass that needs to be kept in storage in order to make sure that there's a continuous supply of biomass to the boiler, to the CHP system. Some quantities need to be kept in storage on the site, and well, let's say depending on the expected maximum supply interruptions from biomass suppliers, a certain quantity can be calculated that needs to be stored on the site. They can have a look at what form this could be stored. This could be either, for example, in the form of wood chips that can be immediately fed to the fuel bunker of the CHP unit. And wood chips have their specific bulk density, in the order of 250 kilograms per cubic meter. And then you would get certain storage volume needed, and assuming a certain average height, you could calculate a certain space requirement for this storage. And this is, let's say, this kind of large bulk is usually stored out in the open. It's also possible to have a part of this stored as solid wood, so let's say as log wood or offcuts, with usually somewhat higher bulk density, and that means that for the same tonnage of storage you may need less volume, and therefore also relatively less space. In addition to that, you could have for a CHP unit, you could have a large silo which could be completely filled up and which can allow the plant to be run for say 1 or 2 days of operation without having the need to continuously prepare the biomass, so that let's say some days of interruption of fuel management, on-site fuel management can be allowed for. It also means that, of course, it's possible to run during nighttime with only let's say a smaller team of operators. Now, if you look at the actual storage requirements, but the actual space requirements, this is an example for a 10 megawatt plant that was the subject of a feasibility study 6-7 years ago for a project in Zambia. We see here that the total area is roughly 200 by 200 meters, about 4 hectares. What you see is a relatively large storage area for logs. You have here an area where logs can be gutted, can be chipped, and then you have a belt conveyor where the large storage of wood chips is done. And you see here in this corner, you see the actual CHP plant. So that's, let's say, less than one fifth or 1/6 of the total area is the actual installations. And of that, let's say the housing of the equipment is only a part, because being taken on by, let's say, the stack and the condensers and the fuel feeding. I looked up some aerial.
Can I have a question?
Yes, of course.
Okay, these are conditions for European countries where moisture is very low, or I'm concerned about how do you cover all this storage, or you keep it in an environment, and what is the moisture aspect?
Well, it's common for, let's say, large storage to have it out in the open without any cover. And if these plants work with fresh biomass, so this plant, for example, it was intended to work with I think about 20% of fuel coming from nearby sawmills and 80% of wood from plantations. Usually when wood is cut, it can have a moisture content of more than 50%. This drops quite quickly in the first weeks. It drops to 40-45%. And in principle, boiler systems can work with wood of that type of moisture content. Also, when you have biomass in the open, what you see is if it has a certain moisture content, let's say 40%, then even when there is precipitation, if it rains, then you'll see that the moisture will stay on the outside of biomass. So even though, of course, having water adhere to the outside of the biomass, its moisture content will increase, but it's not like the water will get back into the biomass. So it's not like you would have, let's say, biomass of 40% moisture content, and after rain you will certainly have it at 50 or 60%. And that also means that, you know, if you have some rain, even if the rain stops and the water starts to evaporate again, then it will dry just as quickly, almost as quickly as it got wet in the first place. You do already also have systems with biomass drying, especially if you have, let's say, a lot of let's say, low temperature heat available from your energy production system. But that is more usually done with systems that are more sensitive to moisture content, like gasification systems. And it's quite common for combustion systems just to work with the biomass at the moisture content that it has when it arrives on the site.
Thank you. Thank you.
So some aerial photos and some indications of the space requirements. This is a CSP unit, a steam turbine power plant, which is not even that far from where I live. It's in a different town called Kuik. It's about 50 kilometers from here. It's a plant with a capacity of 25 megawatts electric. It's situated on a waterway. That means that it can use this water for cooling. You also see that basically this is the power plant equipment over here. These are storage silos, and this is, say, outside biomass storage. Basically, you get trucks with biomass coming in here, and there must be a weighing bridge here, and then they deposit it here, and then from here it's continuously fed to the silos, and from there to the power plant. And this is working, I think, with wood chips from wood industry. So it's not plantation wood, or let's say wood from landscape maintenance. This is the site of the Austrian gasifier. I think I've showed some photos of that during the previous training. It's a 2 megawatts unit somewhere in a small rural town, producing electricity and district heat for let's say, for companies and households also, I think, for district heating network. There's a relatively small storage space. This is, let's say, solid wood, and this is wood chips. I think that most of the chips comes from the area, from the immediate area, from logging operations. And this, because of this limited storage, you also see that the total site size is not very big. It's less than one hectare. This is a site for a biogas plant. Actually forgot where this was. I think it's in Italy, if I'm not mistaken. So you see two circular digesters over here. You see here is storage of some biomass, let's say silaged biomass, which is supplied from the outside of the site, and this is storage of effluent here in this large circular tank. And let's say in relation to the power output, so this is 300 kilowatts, and you could have a relatively larger site if you compare to, let's say, thermal systems So this is actually less than 1 hectare, but it's already bigger than the gasifier site, which has a capacity of 2 megawatts. So let's say in comparison, this one would have a larger area required per unit of capacity. Of course, this depends very much on, let's say, how much biomass is stored on site. It has to do a lot with the scale. Say a bigger scale will result in a relatively lower space requirement, because well, you'll see that say getting larger units will let's say be more efficient where it comes to the footprint of installations. And if you have a system of let's say continuous supply of feedstock, then this will get you a relatively smaller area needed for the storage of the feedstock. Let me see if I have some more. Yeah, I had a few slides on the technical modeling. I think I'll leave that for now because we're already at 9:30. I don't know if is there any further questions on the space requirements? It's actually quite interesting. I looked up all these sites for the purpose of this training, and looking at you know what size with what capacity, and how that results in a certain footprint. So if you know of any sites, you know where to find them, what are the GPS coordinates. It's quite interesting to look it up and to compare to other known sites. Any questions about that?
It's not exactly one question, but I work with a chips factory, and one thing that always I kept in my mind is regarding the self-ignition of the raw material, because normally they store it outside, not so close as I saw in the picture, not so close of the sea. It's about, say, 1 kilometer from the sea. And I would like to ask you about this, about the possibility of out ignition of it.
Yeah, that's a very good one, because it's let's say one of the potential risks, one of the potential fire risks of biomass plants, especially like you say for solid biomass. What you get if you have the right conditions of let's say organic material and moisture, you get aerobic bacterial activities, let's say inside heaps of biomass, and this generates heat. So basically, because of the conditions of the moisture and the presence of oxygen, you get this bacterial activity which increases the temperature inside these heaps, and basically this is something that has been causing fires. It does take attention to make sure that that people are aware of this possibility, and also make sure that they know under which conditions this can occur. And by, let's say, by manipulating heaps of biomass, this can be to some extent avoided, depending, of course, on the quantities that need to be managed. And in addition, it's also a matter of let's say getting your safety measures, your security, firefighting measures in place, so that if fires do start, that they can be fought and fires can be put out. I don't know if that's something that's that relates to this. Did you have a more specific question, Mr. Vlad? Mr. Vlad, are you still there? Okay, so maybe we can continue. Like I said,
sorry, I lost a little bit the sound for a while, but I couldn't understand the overall explanation.
Okay. I was explaining that this auto ignition can indeed occur when the right conditions of let's say the presence of air and moisture and organic material are all present, so that, let's say, aerobic microbic activity can cause temperature increases. Basically, it's a bacterial process, an aerobic bacterial process that takes place under these conditions, and which generates heat, which gradually increases the temperature inside these heaps. And indeed, as you suggested, this can result in auto ignition. It's mainly a matter of, let's say, having the knowledge of these processes taking place and under which conditions, and being able to manipulate, let's say, large stores of wood chips to avoid this. And on the other hand, making sure that you have measures in place to resolve problems. Let's say, for example, to put out fires, fire extinguishing, if it does occur, especially for companies that manage such large quantities of wood chips. It's important to have this in place.
Okay, thank you very much.
Okay, thank you. So I had some sheets on technical modeling. It's let's say quite straightforward. I think when you look at it, it's mainly as a spreadsheet based. You can have a look at the sheets maybe individually if you would like to have some idea on how this is built up. And if you have any specific questions, please don't hesitate to ask them. This is one for an example for a biomass gasification plant. For an anaerobic digestion plant, it would be a bit different, because you'd be looking at let's say usually different types of feedstocks. You have to make your calculations for the digester size, and then the CHP capacity based on the amount of gas that you produce. And this kind of calculation sheet you can use when making the technical assessment of your project. and also it provides some important inputs for the eventual financial assessment when it comes to, let's say, equipment required, energy outputs, feedstock inputs, combine that with the different cost aspects. And you have the, let's say, the main inputs needed for financial analysis. But I'll leave that for now. See if I can easily switch to my next presentation. So, yes, I think this is it. So that's about some operation and maintenance aspects of bioenergy plants. Of course, it's important to realize that there's a very wide range of different types of bioenergy technologies at different scales with different types of feedstocks. So as such, it should always be realized that it will be different for any type of plant, and there can be some general indications which I will be showing you in the next part of this session. But yeah, please consider this this large range and this large variety of operation and maintenance aspects. What is important to realize, and that is, I think, for most energy generation systems, but definitely also for bioenergy systems, is that it's important to optimize the loading rate and the number of operating hours of equipment, and that is for economic reasons, of course. So if you make an investment and you want the system to to operate to its fullest capacity, so that you are able to repay the investment at the best possible time. It's also, let's say, technically more attractive to operate it for extended periods and at a high loading rate. Equipment is usually at its most efficient when it is, let's say, fully loaded or nearly fully loaded. So it means that the relative quantity of biomass feedstock that is needed for producing a certain quantity of energy is less. When it comes to let's say optimizing the loading rate, for example, then grid connected plants that can operate continuously have an advantage. You see in Europe, for example, that it's quite common to operate units for, let's say, more than 7,500 hours per year, just allowing a few hundred hours per year for maintenance mainly. And it's quite common to run them at high loading rates. Look at biogas system for example, where we have a gas engine. It's quite common to run them at about 90% of their capacity. So that is where you usually have the highest efficiency. And similar things, but let's say it's more for a direct economical reason. Let's say steam turbine systems will also be run at a high load rate, so that you get the highest possible output. I should add also that in general, maintenance is, let's say, time bound. So it doesn't really matter that much whether you run a system at 50% or 90% when it comes to the maintenance that is required for a system. So if you then look at the maintenance cost per unit of energy produced, then it will be really a lot lower if you have a system running at a higher loading rate, because the maintenance cost will be the same. The amount of energy produced will be higher in the case of a high loading rate. Let's say in contrast to grid connected plants, you will find isolated plants, let's say connected to mini grids, for example, being operated to supply, let's say, the specific energy demand, and they will need to follow the demand fluctuations that occur in the grid, and it means that there will be daily, possibly also seasonal variations in the plant output. It means that you may have, let's say, lower numbers of running hours and lower average loading rates. Well, one operational aspect that really distinguishes bioenergy units from other renewable energy plants is the let's say the feedstock supply, and let's say the production, supply, and handling of biomass is. It's probably one of the main operational issue that is incorporated in the operation and maintenance of a system. It's important, of course, to make sure that when the plant is operating, that there's that there's biomass available when it is needed, and especially for let's say larger grid connected plants, it really means to have a continuous supply of biomass to the site. So that is supply. Secondly is a certain storage need. As discussed earlier this morning, you need to have a certain minimum stock of biomass in order to make sure that any supply interruptions will not result in shutdowns of equipment. So that needs stock. Further, there is quite often the need to process the biomass. That can be chipping of logs and, say, types of sawmill waste. In some cases, that might include sieving, taking out, say, the very small parts, for example, for gasification systems. Drying may be required, also depending on the technologies that is used, and all in order to make sure that the quality of the feedstock is sufficient for the system. When I say quality, say the main criteria, the main properties are moisture content, the morphology, say the size and shape of the biomass. And then, as the last point, it's important to make sure that the biomass is continuously transported to the fuel hopper of the system. That means that always need to make sure that there's an operator working equipment, so that the biomass can be transferred from the storage to the system, the CSP plants. I say CSP plant now, but a similar thing goes for let's say gasification plants, but also anaerobic digestion plants, also managing of feedstocks. So there's of course different sources of biomass that can be considered.
Can I interrupt one more time?
Yes, of course.
Simple question. To start a plant like this, how long does it take? An hour?
The startup of let's say from a cold startup, you mean?
Yeah, a cold start. Yeah.
Okay. Let's say for a large biomass unit, where you actually have to heat up a boiler, and also to start up a turbine system, because turbines they need to be started up gradually. They need to heat up. They don't immediately start up. This can take let's say hours.
So it's normal that people leave like the boiler at a certain heat if it starts every day.
Well, yeah. Let's say if you have a large boiler with a turbine system, then it's quite common, let's say, not to turn it off at all, to have it run for continuously for weeks or months on end. If you have, for example, engine systems, then it's easier. A CSP engine, you can start it up in minutes. Just need to have some checks, and then start it and connect the load. So let's say for biogas systems, once the digester itself is operational, then starting your engine is quite easy. Starting up the digester itself, for example, that can take weeks or even months in total. So that is also something that you usually do, and it will continue going unless, let's say, it's shut down for large maintenance. So it runs for several years, preferably if there's no technical problems. Gasification systems, let's say smaller systems, can be started up usually, let's say, within half an hour or an hour or so. So if you have a fixed bed gasifiers, let's say a few hundred kilowatts, up to a few hundred kilowatts, it's a matter of let's say basically lighting it, letting it heat up, and let the process start. And again, then if you have gas of sufficient quality, then you can start your engine and start production. So that is usually, let's say, within the hour. But if you have, let's say, larger gasification systems, let's say fluidized bed gasifiers, for example, then this may be longer. You could be looking again at several hours, because the whole system has to be heated up. The sand bed has to be heated up, and this takes more time.
Thank you. Thank you.
Okay, so it's like I said, it's important, especially for larger systems. Yeah, once it's running, to just to keep it running as long as possible. And even if you would have to interrupt the electricity production of a turbine, then the turbine itself will need to be kept let's say freewheeling at the normal operating temperature, so that when it can be taken back in operation, then it's already heated up, and it can start producing again. Okay, so biomass sources. So on the one hand, there's possibility usually in industries that produce byproducts and wastes to use this biomass for energy production. And that means that usually a bioenergy system is more or less integrated in the company, let's say in the factory, in the process. It also means that there's a more or less continuous production of biomass, and that the storage needs are quite limited. And that's there's a very high level of control of the biomass supply. So there's no logistics involved in getting it from one place to the other, to the bioenergy site. And of course, it's usually the same owner. So the one producing the biomass is the same as the one consuming it. Then the second main option is biomass production. So let's say if within the same project you have let's say a system of plantations, for example, for producing either woody biomass or let's say biomass feedstock for anaerobic digestion. Energy maize, for example, is a very common feedstock for anaerobic digestion plants. And that means that this has to be produced externally, or let's say outside the main unit site. And that does mean, of course, that it requires managing the plantation, the activities, the production activities, from planting to harvesting. You may have some decentralized storage of biomass. Then you have the logistics of bringing it to the site. So that really adds to the complexity of the system, of the fuel supply system. On the other hand, it does mean that if it's within the same company or the same project, there is, let's say, a relatively high level of control over the supply. So that is more or less the advantage there. Then the third main option is to have biomass supplied from external sources, and it can be, you know, it can be solid biomass from, let's say, waste or byproducts from other industries. For example, we've been looking at this cashew shell case, and actually this company is supplying its shell to another company that is using this as a boiler fuel. That could be one example. It can also be, you know, a sawmill supplying its wood waste to CHP plants in the area. It can be food processing industries supplying biodegradable waste to an anaerobic digestion plant, and there's all kinds of examples how this works. And this is, you know, convenient on the one hand, because it's something that you don't really have to consider yourself with the biomass production aspects. So provided that you don't already produce the biomass from your main activity, let's say, as is the case in the first option. On the other hand, there is a certain dependence situation, and especially if you have, you know, just one supplier or maybe two suppliers of your feedstock, then this is a risk. You know, this if for what reason let's say the supplier doesn't produce their waste because their factory is under maintenance or has technical problems, and their own production has stopped, then their production of waste and or byproducts has stopped, and it means that this immediately as a consequence for the bioenergy plant. So let's say diversification of supply is something to really look for if possible. Of course, any combination of these three is possible. I think that's also something that you see in larger anaerobic digestion projects. You know, a project owner could, for example, be a large farm or large manure processing company, and they may be looking for, let's say, external suppliers of specific feedstocks from food industry, from food processing industries, to increase the production of their unit. And in order to maximize scale, for example, they could also be producing certain quantities of biomass themselves. Like I said, these types of maize, energy maize, which can be silaged and then used continuously throughout the year, and then you may get a certain diversified supply of biomass throughout the year at the required scale. What is with feedstock? What is a specific concern is feedstock that is perishable. So that's you know that starts to degrade quickly, and it's mainly applicable with feedstocks for anaerobic digestion plants. Some feedstocks, if they have the right structure and the right moisture content, it's possible to produce silage of it, meaning that it's basically chopped to the right consistency, and then let's say compressed as much as possible, so that most of the air, the oxygen is pulled out. Then it's covered to shield it from air. And then you get some microbial activity that produce acids, and because of this acidification, the pH drops to a certain level, then let's say these microbial activities stop, because the conditions for bacterial activity are no longer possible. And this is called silaging. You see here in this photo, you see silage, which is being used. Say the under cover is the silage that is not being used, and once it's open, it has to be, it has to be consumed. You can't keep it indefinitely once it's opened, and then it's gradually fed to the anaerobic digestion systems. On the other hand, for some types of feedstocks, for example, very wet feedstocks, silaging is more difficult, and in those cases, it may have to be used, well, either immediately or at least, let's say, within a day, and it's quite common for well, let's say for very wet feedstocks. For example, wet manure, when it is produced in stables, in livestock stables, and it's if it's kept as such, then it also already starts to degrade and converts to biogas, to methane. And it means on the one hand that the feedstock loses its capacity to produce more biogas. On the other hand, you get the emission of methane to the atmosphere. In those cases, it needs to be fed into the digester as quickly as possible. A second important aspect is not so much feedstock, but let's say diesel. When you look at dual fuel generation systems, so it means diesel engines where you use a combination of diesel and a gaseous fuel. And that can be biogas or from anaerobic digestion, or it can be producer gas from biomass gasification. It's possible, I think that was mentioned in one of the previous sessions, to use this gas in the diesel system, as long as you also continue using some diesel for the ignition of the fuel air mixture, and this means that this diesel consumption can be a let's say a cost component, an important cost component, I should add, because the consumption will, under normal conditions, be, let's say, at least 20% of the energy, and it's commonly it's a bit higher, especially if you have systems with, let's say, low fluctuations. Then you may have to have a higher overall diesel consumption. And as I said, you can't do without when you decide to use a diesel engine. Then it means that you will also always be consuming the diesel as long as you're using it. It does have its advantages, of course. So if you have a system that was already running on diesel, then you can use this gas consumption to reduce your overall diesel consumption, and that is, in practice, that's the most common application of dual fuel. You could have a good loading rate of your gas supply system. So you have you make sure that you have a continuous consumption of your gas, and if there's any peaks, then you supply them with diesel. And if you have a diesel engine, then you already have your fallback, so your backup system in case of any gas interruptions. For example, if there's seasonal fluctuations in let's say in biomass availability, then in high season you can do with maybe only 20 to 30% of diesel, and the remainder coming from your biomass. And if biomass availability is less in a certain season, then you can increase the amount of diesel and still continue your full energy supply. There's a small example. This is the load graph that was included in the case study at the cashew factory. So what could in principle be considered is to use the existing diesel generator and to have a small gasifier, for example, of roughly 40 kilowatts, and operate it for about 13 hours per day. And then you can have a diesel replacement of more than 60%. And it means that's overall you need a smaller gasifier. So instead of having a 100 kilowatts unit, you do with a 40 kilowatt unit. And you would only need the gasifier, so not the gas engine, because you will be using the diesel unit. It's already there. Third important aspect in bioenergy system is staffing, of course. I think also in relation to other renewable energy systems like PV and hydro, you may have a higher dependency on staff. On one hand, because let's say you have staff required for biomass manipulation, let's say for managing your supply, your pre-processing, your stocks, and your continuous feeding to the system. On the other hand, you will need to have an operator. This can be a single guy for a small unit. But if you have a large plant, then because you could have a need to have let's say boiler attendants, you may have an electrician, you may have some continuous maintenance people required to have them on site. In general, as you can imagine, the relative need for staff is lower when you have larger systems. So let's say a 10 megawatt unit will not require 10 times as much staff as a 1 megawatt unit. Let's put it that way. You may have highly automated systems that require relatively a few staff. For example, you can have anaerobic digestion systems at animal farms that just need frequent feeding of the digester. but you know the engine will continuously run, so it doesn't really need much attention, and so it means that overall it could be a matter of a few hours of operating time for a digestive system. You could have plants that are integrated in industries. For example, the one that we've been looking at in the cashew system. We have a continuous biomass supply, so this is something that may require less staff. Of course, if you have a dedicated fuel production, let's say plantations, for example, then you may have quite large staff requirements, let's say off-site, let's say for managing plantations, for harvesting, and possibly for local decentralized processing of feedstocks. And what is quite common is to work in shifts. Say quite common to have 3 shifts and have, let's say, night shifts with fewer staff. Have weekend shifts, say holiday shifts, or you may see holiday shutdowns of systems as well. So that, let's say your total staff requirements may be different from what you would normally have if you count the heads working at any time at the bioenergy plant. I have a small example, let's say, from this feasibility study at the Zambia CHP unit. Over there, it was planned to have, let's say, 10 staff during the 2 daytime shifts, and 3 staff members in the single nighttime shift. So let's say the immediate numbers of staff would be, let's say, 23 in 24 hours. But because of weekend shifts, of sick leave, of that kind of considerations, you may have a total of roughly 35 employees on the site alone. Let's say for the biomass production, that would be a multiple of that. About half of the staff would be involved in the biomass supply and the stock management.
Wow.
Hello? Did you have a question?
No, it was Rosa.
Okay. And then you would have, let's say, some boiler attendants, an electrician, some people working in a workshop for, let's say, for maintenance, small maintenance, daily activities, and you may have say a supervisor, plant supervisor working from the control room. In contrast, if you look at a small unit, for example, in the Netherlands, if you would have a 1 megawatt unit, then you could have, let's say, 2 staff members. But because of the different shifts and the need to have staff working weekends, etc., you may have a total of about 5 people on site. And that is more or less indicating both the scale and the technology, so the level of automation of units. Looking at specifically at biogas plants, you often see them highly automated. So that, let's say the digestive feeding, say apart from the supply of feedstock to feeding hoppers, that needs to be done manually. But once the feedstock is in the hopper, then it's automatically fed to the digester. It's at regular intervals. You have the heating system of the digester to keep it at the optimum control. You have the mixing. It's all automated. So this is all controlled. It doesn't need specific operators. What you do see for large systems that are operated at let's say their peak efficiency, it needs some monitoring of say biochemical process parameters in order to keep it running at this high level, and to make sure that there's no instabilities that could let's say lead to shutdowns of biological processes. Let's say if there's for example a certain level of overfeeding of a digester, then you may have certain groups of bacteria producing too many acids, which may be too much, which may reduce the pH in the system, which could negatively affect the effective operation of other bacteria, and then you get a deterioration of the system, and your digester could stop functioning. And if you always tend to operate your digester at the highest possible feeding rate, then you need to make sure that kind of problems don't occur. That needs some frequent monitoring of the status of your substrate. And of course, if you have very large plants where the feedstock supply is a bit more complex, for example, where you have different suppliers of feedstock, and we have more or less continuous feedstock supply to the hopper, then you may need more staff for this. Other typical activities include, of course, the maintenance of different parts of the system. You need to monitor the effectiveness of your gas treatment system. Say systems needed to remove corrosive elements from gas. For example, they may need to have filter beds exchange, for example, from time to time. This may require the frequent testing or the frequent monitoring, at least, of the decomposition of the gas. And very important for biogas systems is the management of the effluents. So let's say the material that comes out of the digester. It's about the same volume as what you put in. There's only let's say a relatively small quantity of the matter actually gets converted to biogas. You know, there's a lot of water in the feedstock that goes in, and that will come out in the same way. And this feedstock has to be managed as well. I mean, it could be processed, it could be dried, for example, to be marketed as a dry fertilizer. It could also be spread over agricultural fields as a wet fertilizer. Quality needs to be checked so that it can be established what is the actual fertilization value. And the evacuation, especially if you have really large quantities, then you need to make sure that you have the access to the agricultural fields to spread it out on a more or less continuous basis, especially in let's say situations where you have let's say seasonal let's say growth seasons that may have different requirements for certain plant nutrients. Then you may have to actually stock some of the effluents. For example, in Europe, it's usually permitted only to put material in the fields during the growing season. So that's, let's say, all these nutrients actually get taken up by the plants during this season. That means that during the fall and the winter seasons, the effluents need to be kept in storage, or processed and let's say evacuated in a different way. General maintenance activities. I think it was already mentioned in one of the previous sessions. I think I heard Dr. Arans, Paul, to say something about maintenance. You have, let's say, different maintenance categories. You have, let's say, preventive maintenance, which is, let's say, more or less regular maintenance, where you carry out maintenance activities as per a preset schedule. You may have so-called predictive maintenance, which depends on the condition of certain equipment or parts of equipment. And you may have reactive maintenance, let's say, actually when something is starting to break down or already has broken down, then it's replaced or fixed. And that is usually something that you want to avoid, of course, by making sure that your preventive and or predictive maintenance tasks are carried out as required. Of course, here also there's because of the different nature of different technologies and the different scale, different types of equipment used, you can have any types of maintenance requirements. Rule number one is to follow the recommended maintenance, the maintenance activities and schedule as recommended by the manufacturer. Also needed in general to be able to fall back on warranty conditions specified. Say if your equipment is not maintained correctly, then warranty is usually void, and any problems, any technical problems will have to be resolved at the cost of the plant owner. Second point is to make sure that there's always access to spare parts and consumables needed for maintenance. So that there's no, let's say, interruption of maintenance, of required maintenance, because you're waiting for spare parts that are still being in process of being shipped out. Very broad indication of maintenance schedules. What you usually see for systems is that you have your frequent maintenance, let's say, with daily or weekly or monthly tasks carried out by maintenance staff, let's say plant staff. so that's frequent or small maintenance. You see for larger equipments like engines, like turbines, to some extent boiler equipment, that you have, let's say, so-called minor overhaul and major overhaul, meaning that, let's say, for minor overhaul, you get equipment open up, inspected, with some small parts being replaced. And with major overhaul, let's say it's a larger operation. It also gets opened up, and let's say more parts are replaced. And let's say overhaul activities are generally carried out by specialized companies or let's say manufacturer staff coming to the site for the overall activity. Boilers, yeah, maybe I can skip through the next parts a bit quickly. Especially large boilers, you know, they require visual inspections daily. So fuel supply systems, ash removal systems may need, let's say, a small replacement of parts and lubrication. On the inside of boilers, you have say surfaces that may get fouled by ash or other deposits, and that's may require cleaning. And let's say during operations is not possible, of course, unless you have systems integrated that can blow away deposits as long as they're not melted to the surfaces. Let's say on large maintenance, you will get inspection of the inside, repairs of refractory, inspection and repairs of boiler pipes, or to avoid them to form weak spots where you may get problems with, let's say, explosions under pressure. Servicing of auxiliary equipment like fans, pumps, grates, cleaning of grates, removal of ash deposits. And grates have a limited lifespan. They may need replacement after a certain number of years. Turbines, as indicated, you have your overhauls every say 3 to 4 years, assuming more or less continuous operation. Let's say minor overhauls and let's say major overhauls after 5, 6, 7 years of operation. You may have annual inspection, endoscopy to look at specific wear on the inside, and let's say daily inspections are mainly focused on making sure that lubrication systems are functioning correctly, that any supply valves and safety valves are functioning correctly, and that any systems for identifying fault conditions are in operations. So that if any abnormal conditions occur, that you may get the right alarm systems or automatic shutdown procedures. yeah, electrical systems, other equipment. Maybe you can go through that yourself, because we're starting to run out a bit. Engines usually get engine maintenance sheets defining how often lubrication oil and filters need to be replaced. Spark plugs in case of forced ignition systems need to be replaced frequently. You get also here you get a minor overhaul and a major overhaul with different typical replacement of parts. Digesters, biogas systems. Let's say on the outside, you may have daily checks of damages to the system, insulation on the outside, corrosion, and resolving this. You get after a few years, you may have a need to service or replace internal mixers, especially when they're submerged on the inside of the digester. You may have the total tank, digester tank, emptied out in order to remove, let's say, layers of sediments from the bottom. Which is a major operation. It needs to it requires the startup afterwards. It's indicated that can take weeks or months to complete again, but that is using an operation that is done once every few years, so not an annual activity. You have, let's say, maintenance and checks of your gas cover, where the gas is collected and stored. Inspections, checks of gas piping and the heating systems of the digester tank, and frequent checks of the control and instrumentation systems that monitor the conditions inside the digester. So that is the part on the operation and maintenance. Are there any specific questions on that? Let me see if I can start up the next. Any questions? Okay, well then I'll continue with the next part, and that's on environment, health, and safety. Let me see. So I'll start with the general environmental aspects of bioenergy systems, some health and safety, and some social aspects. I think I should be able to finish this in 25 minutes. The environmental aspects. Well, the first things that we take into consideration with renewable energy is, of course, the greenhouse gas aspect. Let's say for other types of renewable energy, solar and hydro and wind. This is quite straightforward. Let's say the electricity produced when it's connected to the grid, for example, then you replace electricity that might not have been produced sustainably. This which may otherwise have led to to the emission of greenhouse gases. For bioenergy systems, it's a little bit more complicated because we're looking at the so-called short carbon cycle here. That means that the emission reduction, greenhouse gas emission reduction, is related to the fact that the CO2 that is produced by combustion, eventual combustion of biomass, or say produce a gas or biogas, is let back into the atmosphere. So it means that's looking at the direct boiler or the engine connected to the bioenergy system. You will have a certain emission of carbon dioxide to the atmosphere. But this carbon that is released to the atmosphere is the same quantity that was taken out of the atmosphere in the production of the biomass. So instead of looking forward to the system where you avoid a certain amount of greenhouse gas being emitted, you look backwards to the amount of carbon, of CO2, that was taken out of the atmosphere by the biomass that is subsequently used for energy production. That is what they call the short carbon cycle, and that is in contrast to the system of, or let's say, the fossil energy system, where the carbon that is being emitted was stored during a very long period of time, and then fossilized, and then being taken from the underground storage, let's say from coal deposits, from oil fields, and then used at a very high rate, so that the net emission of carbon dioxide to the atmosphere is out of balance with the removal of CO2 from the atmosphere. It's important to realize that this capturing of CO2 by growing plants out of the atmosphere is being done under the usage of solar energy. So basically, plants use sunlight for growing. So you could say that that the bioenergy is ultimately also solar energy, but having biomass as an intermediary product. And I should add that it's not as efficient per surface unit as solar voltaics. But of course it has other aspects, other advantages, other features that solar voltaics may not have. For example, the use of it for heat production, which is more efficient than when you would be using biomass for, let's say, more efficient when using, for example, electricity for heating, and the electricity could have been produced by PV systems. But in those cases, heating with biomass would be more efficient let's say technically and definitely financially. So that is the short carbon cycle. What is important to realize is that during the harvesting and the processing and the transportation of biomass, you also have energy consumption, and that means that in the cycle there are some leakages. So it's not a completely closed cycle. You do have some CO2, some net CO2 increase in the atmosphere, but it's a relatively small if you compare it to the complete cycle. A second point that is important when looking at the greenhouse gas aspect with bioenergy is methane. As you may know, methane is a very strong greenhouse gas, a lot stronger than the CO2 actually, and about 20% of the total greenhouse gas emissions is from methane. Now, this methane is produced in industries and in agriculture and from natural sources as well, in swamps and in other systems where you have let's say microbial activity converting organic matter to methane. And to some extent, in some sectors, this methane emission can be avoided by capturing it. For example, by extracting landfill gas from landfills, by using biogas systems in industry and in livestock systems, so that this methane emission can be reduced. Now, looking at just the greenhouse gas aspect of this methane, it could be a solution to flare gas, just to burn it without using it for energy, so that at least the methane is converted to CO2, and this is therefore well, a lot less harmful than the original CH4. But of course, if this methane can then be used for energy production, then you have on the one hand you have let's say a value for your gas by let's say producing energy and selling this energy. You have a stream of income for your project. And on the other hand, you also have the potential replacement of energy that would otherwise have emitted greenhouse gases for its production. I should add that there is quite recently, and there's been a lot of criticism on the application of bioenergy and the denomination of bioenergy as being say greenhouse gas neutral. I will give some examples of what is being stated. That is that, like I said, you do have CO2 emissions from biomass combustion. So if you really look at the boiler or the engine, then indeed during operation they emit CO2. And let's say looking at a per gigajoule basis, then this can actually be higher than for fossil systems. It's on the one hand that has to do with the with the scale. So let's say if you look at a coal power plant of, say, several hundreds of megawatts. Then you have a much higher efficiency than if you look at a, let's say, a 5 or 10 megawatts CHP plant. On the other hand, it has to do with the properties of biomass as a fuel and its heating value. And let's say if you only look at the emission side, then this would in principle be correct. But that of course overlooks the fact that this biomass actually took the CO2, the carbon from the atmosphere in the first place. And of course, it's still important to make sure that once the biomass feedstock has been used, let's say it's also new biomass feedstock is being produced for, let's say, future consumption of the bioenergy plant, and not that, for example, you'd be cutting down forests for wood fuel generation, using it for electricity production, and not replanting, for example, because then, in fact, there would be a net increase of for greenhouse gases to the atmosphere.
Como ha comentado antes Alex, se activan técnicamente unos cuantos.
A second point that is claimed sometimes is that biomass is a very inefficient fuel because of its low energy content. This is true to a let's say a very small extent. If you have very long transport lines, for example, if you produce wood pellets or wood chips in the United States and transport them by ship to Europe, then you have, let's say, relatively larger leakages, like I explained in the previous one. These leakages due to harvesting, processing, and transport. But even in that case, you're talking about, let's say, 5 or 10% usually of the total greenhouse gas emission reduction. And if you have let's say a more local system where, let's say, within an area of, let's say, within a distance of 50 or 100 kilometers, then this is negligible. This is just a few percent of the total at most. Third point is which is often indicated that, you know, it takes a very short time to burn biomass, and it takes a very long time to grow biomass. Now, this again is true, but if you make sure that you don't get any over exploitation of forests or other production systems, then this is not a problem. If you allow the time, if you have the space available for the production of the biomass, then it doesn't really matter that much if it takes 30 years for biomass to mature. Then you just have to make sure that you don't use, let's say, more than 1/30th of the biomass supplied in a certain area for energy production, so that you always have a large area of plantation, for example, to grow your biomass, and to harvest only small areas on an annual basis. And then the fourth point is that the exploitation of biomass can lead to destruction of natural forests and reduction of biodiversity. And this is something That is not common, but it's not unheard of either. And this is why it's important to always look at sustainability criteria for biomass feedstock production. So making sure that, for example, that you don't touch natural forests. Make sure that you don't. That's when you produce, you don't overexploit. Make sure that you first use your waste, your byproducts, so that you don't need to grow or get materials from the forest in the first place. Also to look at forestry systems, for example, where a lot of biomass comes from. Make sure that overexploitation doesn't take place over there. That's use of biomass of wood from natural forest is reduced to a maximum in those industries where you get your biomass from. Looking at greenhouse gas emissions, sustainability issues, as indicated, are extremely important, and that is, as I just indicated, consider the use of waste and byproducts first, which could otherwise have deteriorated, let's say, naturally, and actually contribute to the greenhouse gas emission by emitting methane. Protection of primary forests, protection of biodiversity, applying criteria for let's say land use change, making sure that no primary forest is being cut for the establishment of wood plantations, biomass plantations, and also to have, let's say, minimum performance criteria for bioenergy plants. And these criteria are more or less being applied in the European Union, and I think that these should be considered more or less the minimum to be considered worldwide. Of course, when it comes to, for example, minimum performance criteria, that depends on from country to country how you apply them, from technology to technology. Now, what should be added as well is that if you have so-called, let's say, modern bioenergy, bioenergy systems addressing energy needs that are currently being addressed by, let's say, traditional bioenergy. We're talking about mainly household biomass consumption for cooking, for example. Modern bioenergy can actually contribute to a reduction of unsustainable wood consumption. There's a lot of biomass being taken out of forests, being used for charcoal production, for example, in very inefficient ways. And by applying, let's say, modern bioenergy techniques, can greatly improve the efficiency of let's say, charcoal production, for example, the efficiency of cook stoves. And this can greatly reduce the consumption of wood fuels from these consumers. You could look at the production of alternative biomass fuels. So let's say using waste and byproducts from industries rather than wood taken from forests. And you can look at alternative cooking fuels altogether. For example, which is done by introducing biogas technologies to households for producing biogas for cooking and lighting, but also producing ethanol from let's say starch and sugar, or starch and sugar byproducts from industry, and use the ethanol in dedicated ethanol cooking stoves, and then again, let's say avoiding the use of unsustainably produced fuel wood and charcoal. Some other environmental issues, I think I'll just leave that one for now, as we're starting to go close to 11. Health and safety aspects. In general, of course, health and safety is very important to address, because it needs to safeguard the well-being of plant staff and say any other people, either on-site or off-site, say bystanders, avoiding injury or sickness because of exposure to unhealthy conditions. The basics is to prevent unhealthy or unsafe situations. To some extent, this can be achieved by getting the proper design of your systems, of your plant, of your project. Secondly, it can be achieved by having a specific health, safety, environmental policy in your project or your company, including a good assessment of all the risks and risk mitigation, and let's say the possibilities of reducing the potential outcome of unsafe situations. Have proper staff instruction, let's say operating procedures under normal conditions or under let's say unforeseen conditions like fires or like cases of accidents or injuries. So staff should be well aware how to act under those circumstances. And of course, proper maintenance is key in order to avoid equipment from breaking down and causing unsafe situations. I had some interesting parts from the biogas. There's a very nice publication on health and safety in biogas plants. It's from the German Biogas Association. I think that the link can be found quite easily, or I'll circulate that. You can have a look for yourself on the different issues there. It has a very good indication of health and safety aspects in biogas plants, and how hazards can be assessed, how unsafe situations can be avoided by, let's say, by design, construction of system, but also by making sure that the organizational aspects are approached in a way to avoid unsafe and unhealthy situations. Specifically for gasification, there was a project, an EU supported project on the identification of typical say gasification related health and safety risks. You should be looking at, let's say, a potential prevalence of let's say emissions of toxic gases, particularly carbon monoxide is an important one, but also liquids, for example, cooling liquids. And there could be risks of explosion due to the buildup of gaseous gaseous compounds in the presence of oxygen, and the prevalence of an ignition source. Apart from explosion, you could have fire hazards, and major cause, or let's say a potential cause could be operator failure due to the operation of the system by let's say untrained, unskilled, unauthorized staff, or the absence or insufficient presence of operational procedures. Solid biomass plants, well, there you have a very common problem is with biomass supply. Let's say supply vehicles, vehicles that manage stocks on site. That might be running backwards and maybe running into staff. An important one is the storage and handling of biomass. That was one of the things that we discussed earlier this morning. Let's say the potential fire that could start, that could originate from stocks, from heaps of biomass. Dust explosions are quite, well, I shouldn't say quite common, but let's say potential causes of explosions in biomass power plants. And you have your, let's say, your more general potential hazards due to, let's say, systems used for the transmission of heat and steam, transmission of electricity. It's a general fire and explosion inside plants, chemical hazards due to, let's say, the presence of chemicals for example, treatment of boiler water, or for the reduction of nitrous oxides, or the management of fly ash, for example. These all have to be treated as chemical compounds that need to be treated with care. I had a nice small video from the Netherlands that was a small biomass CHP plant in the south of the Netherlands. And in 2007, there was an incident that was caused by a fault inside the boiler. There was a rupture of pipes that transported thermal oil throughout the boiler. That was probably due to insufficient maintenance, and this rupture of this pipe caused the oil to leak into the boiler, which then led to increased temperatures, and then to the complete destruction of the boiler and the whole plant. I think it was only 3 or 4 years in operation, and was a near total loss that we rebuilt from scratch. And then, ironically, only 3 or 4 years ago, there was another incident due to a dust explosion at the same plant, and that caused, well, not the same level of damage, but it was also a cause for the system to be taken out of operation for a few months. There were a few hundred thousands of dollars of damage. So this is after the fire had been put out. On my last sheet, I think this is the last sheet. The social aspects specific to bioenergy. So more than PV systems or hydro systems, is that you may have, let's say, a certain economic advantage related to the supply of feedstocks. For example, the production of feedstocks can create employment in a certain region. It can be for large plants. This can easily be hundreds of full-time staffers. Second point is that materials that might otherwise have been considered as waste are actually utilized, and thereby are given a certain value as an input for energy production. So that actually adds value to the agricultural value chain. The third point is that let's say energy supply costs can be substantially lower in comparison to existing systems, and that can be particularly so for, let's say, remote areas where you may otherwise have let's say a supply of fossil fuel sources, for example, over long distances. You may have a certain value, useful application of wastes and byproducts from bioenergy production. For example, the effluent from bioenergy systems, as mentioned, that can be used as fertilizer in agriculture. And there may be certain sanitation advantages that can be marked as socioeconomic advantage. Let's say basically treatment of certain wastes, organic wastes, and wastewater that might otherwise have been injected to the environment, so untreated or with insufficient treatment. But of course, there are some potential drawbacks as well that need to be addressed when, or that need to be considered, at least when looking at the bioenergy projects. Let's say local environmental issues. For example, if you have a need for producing biomass, let's say purposely producing biomass for energy purposes, it's important to avoid the use of forested land, for example. You might have certain emissions from bioenergy systems, let's say specific wastewaters that need to be considered, including, for example, these effluents that might be earmarked as fertilizer. and that can be beneficial when used as such on agricultural lands. But if they are not used in this way, and they are, for example, just dumped on a certain site, then they can be harmful for the local environment. And what is important is to consider the potential extraction of nutrients from agricultural cycles. So let's say when using byproducts from agriculture that would otherwise have been left in the fields, and let's say the nutrients from these feedstocks would otherwise have been flowed back into the soil. If this biomass is all taken out, let's say year after year continuously, then you may extract more nutrients from the soil than that can be regenerated in a natural way, and that leads to a degradation of the soils. The land usage, as mentioned, and the potential for land grabbing, for the production, large-scale production of biofuels, whether that's say liquid biofuels or solid biofuels, whether it is for local use or for export, it should be avoided. And lastly, there is the food versus fuel issue, where let's say biomass feedstocks are being used for energy production or for fuel production. That take particular materials out of the food supply chain. For example, if there's a large pool of ethanol producing facilities on maize, for example, or cassava, then this could lead to a relative shortage of such material for food consumption. And shortages tend to have a price increasing effect. And there were some instances, although there were incidents, I think 10 to 12 years ago, and there were large food hikes. I think in Mexico, when let's say American ethanol producers started buying maize, large quantities of maize in Mexico, and this led to this effect of food price increase for local consumers. And this then, also led to the debate on whether we should be considering products like maize, but also like oils and other fatty materials for the production of biodiesel, for example. But we should be considering these for energy production in the first place. So that's it for today. Thank you for your attention. It's already quarter past. Sorry for taking more time than anticipated. I'd like to address one final point, and that's about the main questions, let's say the forums with questions and live cases. I'd like to ask you once more to submit your questions and cases. So far we received, I think, 6 or 7 participants, and we'd really like to have some more. So if you can just take 5 or 10 minutes to think of some specific questions.
Yeah, but I have one question. What is the influence of the cost of biomass on the final price of the energy produced?
That's a very good question. I think I'll include that in the next session.
Okay.
It varies, of course, because let's say in some cases the feedstock, when it has to be produced, it has a relatively high price per energy unit. In other cases, you might actually have you know, a gate fee, let's say, accepting types of bioenergy, for example, for energy production, for let's say organic waste, for example, from you know, what is collected from households or from markets or other sources. Then you know, you get an actual processing fee. So you have a sort of negative price, so to speak. But I'll include that in the next session on when we're looking more on some of the feasibility aspects, and try to make some comparisons between bioenergy and other potential energy sources to show the differences in the build-up of the production costs. Any other questions for now, or questions on the let's say the request for or let's say our request to you to submit your questions, your forms with questions and live cases for our final sessions?
Linking to this question, in fact, I would like to address you one issue. In the past, here in Mozambique, we got one program called Jatrofa. Jatrofa was one raw material to produce biodiesel. And on this time, some considerations comes. One is already, you already replied on economic aspects, but the other one is also on environment impacts, because to produce this kind of raw material, we need to use tractors that there is emissions of CO2. And how can we make the right balance on this to justify?
Yeah, let's say the case of Jatrofa was actually very interesting, and actually I used to work at an NGO until about 8 years ago or something. That was created originally in 2005 at the peak of this Jatrofa hype, because it you know, it was a hype. You know, at some point everyone wanted to do something with Jatrofa, because it was considered a sort of a miracle crop that could really produce very large quantities of oil per hectare with minimal inputs, and it could survive long periods of drought, etc. And this NGO that I work with, and try to, you know, actually get a better idea of how this Jatrofa actually how it actually performed in real life, let's say on plantation, because it at some point was all about scale. You know, the plant was mainly used as a hedge, because animals wouldn't chew it, so you know they would leave it alone. So it was a quite interesting plant to make hedges. And then it was seen that, you know, these fruits they produce these seeds, and the seeds contain a lot of oil, and the oil cannot be eaten, so you don't have this food versus fuel discussion. But then it appeared that although these Jatrofa plants they survived under, let's say, difficult conditions, they didn't really perform very well unless they were actually, you know, planted on good soils, frequently fertilized. They did get sufficient water, then you could optimize the conditions for the productivity. Then you could actually get, you know, maybe a ton of oil per hectare under very good conditions. Which I should add is,
sorry to interrupt you, and also you're using tractors as well that use diesel.
Well, you know, even using mechanical equipment isn't such a problem if your overall yield is high enough. Let's say if your yield is, for example, a few tons of oil per hectare, and you use maybe let's say a few dozens of liters, or even 100 liters per hectare per year, which is a lot, of course. Then, you know, then there is a certain justification for that. But if your field only produces 100 liters or 200 liters of oil per year, and you already use 50 or 100 liters of diesel for producing it, you know, then you don't have a net advantage. You could even, you know, consider using the jatropha oil as a tractor fuel, because it's quite a good vegetable oil. And if it's well filtered, and you make a small modification to the diesel engine, then you can use it directly. So you wouldn't be using fossil fuel in the first place. But then again, you need to have sufficient production to actually cover the energy demand for not just the tractors, but also, you know, for the fertilizer, because fertilizer production itself also consumes energy. And so for the whole processing of the jatropha, it only works if you really have a well-performing production chain. And with jatropha, it has appeared that, you know, these extrapolations of production from, let's say, incidental of individual plants could not be made to larger areas without really losing a lot of production. So it was, on the one hand, it was overestimated as because of, you know, lack of knowledge. On the other hand, there were also instances of, you know, wishful thinking, and project developers sort of, you know, painting a too optimistic picture of the performance of jatropha. I don't know if there's still any jatropha projects left in Mozambique. I think worldwide it has more or less stopped. Most of it more than 10 years ago.
Also here, it's already stopped.
Yeah, I visited a project in the north of Mozambique, with a project by an NGO called ADPP, to work together with the NGO that I worked with back in the past. And, you know, it was the same problem there. There were high expectations of the yields and the production, and the, you know, all the economic benefits for farmers that could have an additional crop that would be low maintenance and high yielding, but that just didn't work in practice. So I think, you know, globally, most projects were abandoned. Maybe some research activities have continued for getting, let's say, even better yielding plants that might in the future maybe used for larger scale, better performing jatropha projects. But that, as far as I know, that hasn't been applied in any commercial scale plantation.
Okay, thank you very much.
All right, so I think we can close for today. Again, thank you very much, and please remember that the next session by Dr. Arans, by Paul, is tomorrow instead of Wednesday, because Wednesday I understood was a public holiday in Mozambique. So next session is tomorrow at 9 o'clock.